Hi everyone. So last time we have talked about the chapter 3, some part of chapter 3. So these are what we've done last time. So today, briefly, we're going to review what we've done last time, and then we're going to solve some the example problems from our textbook, and later we're going to talk about the nominal and effective interest, followed by continuous compoundings as well. Okay. So last time we've addressed the time value of money with this very simple question. And because the money is much more valuable today than in the future, people are willing to pay interest to have money available for their use, right? So I do say the interest can be considered as a rental fee for money. And interest is a fee paid for the use of money, or it is a fee earned for the use of money. And last time we have also learned two types of interest: simple interest and compound interest, right? And the calculation of simple interest is only based on the initial principal amount. So the interest rate is simply multiplied by the number of years. But I should let you know that this simple interest should not be used in the engineering economy problems. Okay? In other words, in this class, we are much more interested in the compound interest. And the calculation of compound interest is based on the current unpaid balance that includes the principal amount and any unpaid interest from the preceding period. Okay? And last time, we have also talked about equivalence. Equivalence is an essential factor in the engineering economic analysis. So like it says here, using the concept of equivalence, you may convert different types of cash flow at different points of time to an equivalent value at a common reference point. And equivalence is dependent on the interest rate. Okay? And in order to facilitate the equivalence computation, we use this notation and use the single payment compound amount formula, especially to find a future sum of money given the present sum of money in this case. And this formula represents a relationship between the present sum of money and its equivalent future sum of money, right? And last time I also mentioned that this equation 3-4 is another expression of equation 3-3. We've also used the single payment present worth formula to find a present sum P given a future sum F. Okay? And equation 3-6 is another expression of equation 3-5. Okay? Okay. Now, let's solve a couple text example problems. So the first example for today is 3-5. Okay? So if $500 were deposited in a bank savings account, how much would be in the account 3 years hence if the bank paid 6% interest compounded annually? So we are solving example 3-5, right? So $500 were deposited in a savings account. So if you want to draw a cash flow diagram, arrow pointing down means the negative cash flow because you are going to pay $500. It's going to be like this, right? For 3 years. And it pays 6% compounded annually. So I is going to be 6%. 0, 1, 2, and 3. And we want to find the future sum at the end of year 3, right? So given the present sum P, which is 500, the future sum F can be found by using the equation 3-3, right? So we are going to use equation 3-3, which is F equals P times 1 plus I to the power N. So if you use the real number, it's going to be P equals 500. 1 plus I is 0.06. N would be 3, right? And equation 3-4 is another expression. So if you want to use it, it's going to be P F given P at I over N period. So it's going to be 500 times F given P, 6%, and 3. And actually, we can get this value, which is called single payment compound amount factor. This factor value can be easily found from the appendix B. So we are looking for 6%. It's very small to see, but so we are looking for 6%. So you need to find 6% here as the interest rate per compounding period. And we want to find a future sum F given the present sum P. So we are looking for F given P, which is the first column, right? And the number of compounding periods are 3 years. So if you look at the rows corresponds to number 3, you can find the value of 1.191 here, which means this factor value would be 1.191. Okay? So just using the Excel, this value is my $595.50. Okay? This is the example 3-5. How about example 3-6? If you wish to have $800 at the end of 4 years and 5% interest rate will be paid annually, how much should you put into the savings account right now? So you wish to have $800 at the end of 4 years, and you'd like to know how much should be deposited in an account that pays 5% annually. So from the problem description, you can get the future sum would be $800, and the interest rate would be 5%, and the interest period is 4 years, right? So the present sum can be found by the formula again. But let's draw the cash flow diagram first. So we want to find the present sum, P, right? Zero, 1, 2, 3, given the future sum of $800, and we are going to use interest rate of 5%. Okay. So using the single payment present worth formula, which is P equals F times 1 plus I to the power negative N equals 800 times 1 plus 0.05 to the power of negative 4. And we also learned that this is another expression, P given F at I% over N periods, which is 800 times P given F I%, sorry, this is 0.05, right, over 4 periods. Again, this factor value can be easily found from the Appendix B of our text. So we are looking for 5%. So here, this page 608 provides the compound interest factors for 5%. Okay, and we want to find a present sum P given the future sum F. So we are looking for the P given F, which is the second column here, and corresponds to the N value equals 4. So it's going to be 0.8227 as the factor value. So this is going to be 800 times 0.8227. Okay. So using the maybe your calculator or Excel that I'm going to use, this value is $658.16. Okay, so this is the answer for example 3-6. Next, let's talk about example 3-7. Okay. Suppose the bank charged the interest policy in example 3-5 to 6% interest compounded quarterly. not annually. Okay? So for this situation, how much money would be in the account at the end of 3 years, assuming a 500 deposit right now? Okay, so $500 were deposited in the savings account, pays, okay, is example 3-7. $500 were deposited in a savings account and pays 6% annual interest. Compounded quarterly. For how many years? For 3 years. Okay. So the given 6% interest is an annual interest rate. And because we are dealing with 4 interest periods per year, the interest rate per interest period would be 6% divided by 4, which means that for 4 years and for 3 years, there are 12 interest periods, right? 12 interest periods. Right? So we are going to use n equals 12. Okay? So does that make sense? So I said because we are dealing with 4 interest periods per year, because it is compounded quarterly, the interest rate per interest period would be 6% divided by 4 quarters. So for 3 years, there are 12 interest periods. For 3 years, for 3 years, there are 12 quarters. That's why we are going to use n equals 12. Okay? So if you want to draw the cash flow diagram, it's going to be P equals 500. And 0, 1, 2, 3, 4, 5, and let's say this is 11, 12. Okay? And the unit would be quarters this time. And we want to find the future sum, F, at the end of 12th quarter, right? And the interest rate would be 6% divided by 4, which is 1.5%. Okay? So using the formula, we can get the future sum. These are 500 times 1 plus 0.015 to the power 12, right? Using another expression, P sorry, is F given P I% over n periods, which is 500 times F given P 0.015 over 12 quarters, right? Again, using the appendix B, we can get this vector value. So we are looking for 1.5% and F given P over 12 years, over 12 quarters, so it's going to be 1.196. That's the vector value. 1.196. So how much is that? It's going to be $598 even. Okay? So this is the answer for example 3-7. So the example 3-7 is the advanced problem, right? Okay, then here's another example. So consider the following situation where the borrowing of P is repaid in 2 payments. At the end of year 3 or at the end of period 3, you're going to pay $400, and at the end of year 5, you're going to pay $600, right? So here now we need to solve for P, assuming 12% interest rate and using the compound interest tables. So according to this cash flow diagram and the table of cash flow, we know that the present sum P would be the summation of these 2 future values, 400 at the end of year 3 and 600 at the end of year 5. So by using the single payment present worth formula, we may obtain the present sum P value. So in this case, the present sum P would be 400 here, P given F, and 12% at the end of year 3, plus 600 P given F, again same interest rate of 12% at the end of year 5. Okay? And by using the compound interest table, you can get those 2 factor values. So we are looking for 12%. So here's 12%. The page number 614 provides the compound interest factors for 12%. And we are looking for P given F. So there is a second column. Over period 3 would be 0.7118. Over period 5 would be 0.56 0.74. Okay. So in this case, what will be the answer? According to my previous calculation, is $625.16. Okay. Okay. Now, let's talk about the nominal interest rates and effective interest rates. So we have learned that the interest rate and the number of periods must use the same length periods. Both must be in years, in quarters, in months, in weeks, and so on. Okay? Now let's talk about what you need to do if compounding periods are shorter than a year. Actually, we just solved one problem. Example 3-7. In this example 3-7, the given interest rate, the annual interest rate was compounded quarterly, right? The quarter is shorter than the year. In such case, we need to think of the advanced step like this. Okay? So we're going to talk about this more in detail right now. Okay? So very often we want to compute monthly loan payments or the amount in a savings account that accumulates monthly deposits. In this case, the interest rate will probably be stated as R% per year with monthly compounding, because there are 12 months in a year. In such case, M's going to be 12. Okay? So for example, a common credit card rate is 18% per year, compounded monthly. To generalize this for different lengths of periods, we will use this notation. Here, the small r is the nominal interest rate per year that is not adjusted for compounding. You know, in each compounding period, the interest is compounded, which means that it is computed and then added to the total amount of money deposited or owed. Here, small I is the interest rate per compounding period. And small m is the number of compounding periods per year. Okay? Now we add effective interest rate, which is small I sub a, which does adjust for compound interest to the previous notation. So if two nominal interest rates have different numbers of compounding periods, you cannot compare them directly. However, each combination of a nominal interest rate and the number of compounding periods corresponds to an effective interest rate. And because these effective interest rates include compound interest, they can be directly compared. And here, if m equals 1, what happened? If m equals 1, then this I becomes R. So we may say that the nominal interest rate is equal to the effective interest rate. Okay? If a nominal interest rate is compounded annually. Is that right? So we will talk about continuous compounding later. And now just I'd like to let you know that the annual interest rate for continuous compounding can be obtained by this formula. Excuse me. And this table compares nominal interest rate with the effective interest rate for a range of compounding frequencies. Okay? It's compounded yearly, compounded semi-annually, compounded quarterly, compounded monthly, daily, and continuously. Okay? So here, if you increase the frequency of compounding from year to daily, for example, what happened? The effective interest rate is increased as well. Of course, this change will have a huge impact if you are dealing with a huge amount of money. Okay? Okay. Now let's talk about example 3-10. A loan shark lends money on the following terms. If I give you $50 on Monday, you owe me $60 on the following Monday. So, in that case, what nominal interest rate per year is the loan shark charging? So, how much did they charge for interest? $60 minus $50, which is $10, right? $10. Which is from 60 minus 50, right? What is the interest period in this case? A week, right? Weekly interest rate. So I do say weekly interest rate is how much? Is 20%. How do you know that? 60 minus 50 divided by 50 becomes 20%. Okay? 10 over 50, which is 1 over 5, is a 20%. 0.2 becomes 20%, right? So I do say they provide weekly interest rate of 20%. So how to get the nominal interest rate per year in this case? So we've learned that R is the nominal interest rate per year that is not adjusted for compounding. Okay? And I is the interest rate per compounding period. interest rate per compounding period. So in this case, it is going to be 20% per week. Is that right? Then what about M? M is the number of compounding periods per year. Number of compounding periods per year. So what is that? How many weeks do we have in a year? 52 weeks, right? So M would be 52 because there are 52 weeks in a year. So using the formula, I equals R over M. Here I is 0.2, M is 52. So R is 0.2 times 52. What is that? 1,040%. Okay? So my recommendation would be never ever borrow money from this loan company. Okay? Okay. Then what about the next question? What effective interest rate per year is he charging? So from part A, we know that R, the nominal interest rate per year, is 10.4, which is 1,040%, right? And M is 52 weeks, right? Now, using the formula, which is I sub A equals 1 plus R over M to the power M minus 1, which is 1 plus 10.4 divided by 52 to the power 52 minus 1. Okay? So from my previous calculation, it is 13,105 minus 1, which is 13,104. Okay? So what percent is this? It's 1,310,400%. Okay? See, I told you. Don't borrow money from them. Okay? You'll be in big, big trouble. Okay? So using the weekly interest rate, 20%, we can obtain the same value. So using different formula, I sub A equals 1 plus I to the power M minus 1. Here, 1 plus I is going to be 0.2, right? And M is 52 minus 1. I believe this would be the same value, 13,104, which is same as this. So 1,310,400%. Okay? Okay. Then what about the last question in this example? If the loan shark started with $50 and was able to keep it, as well as all the money he received, loaned out at all times, how much money did he have at the end of 1 year? At the end of 1 year. Okay? So if you drew the cash flow diagram, so $50 right now, you borrow $50, right? And then at the end of 51, and let's say 52 down here. At the end of 52, how much money did he have at the end of 52 weeks? At the end of 1 year. So in order to get this future sum of F, you can use this formula, which is 50 times 1 plus 0.2 to the power 52. And from my previous calculation, this is going to be $655,200. A lot of money. Okay? Okay. Next is about the continuous compounding interest. So it is possible to let the number of compounding periods approach infinity, okay, which is called continuous compounding. And these are the formulas related to the continuous compounding. Also, as stated earlier, effective interest rate per year is like this. And I'm not going to go through all the details of how to derive all these formula in class. So please read through our text in pages 93 through 94. Okay? Okay, so using this formula, we are going to solve example 3-11. Okay? So if you were to deposit $2,000 in a bank that pays 5% nominal interest compounded continuously, how much would be in the account at the end of 2 years? So using the formula for the single payment compounded amount would be F equals P, F given P at R over M period, which is same as P times e to the power R times N. Okay? So here, from the problem description, R is given as 5%, N is given as 2 years. Is that right? So 2,000 times E2 0.05 times 2. Excuse me. And this is $2,210.40. Okay? Okay, let me just double check it. Also, we can use different formula, which is this formula, effective interest rate per year. We can get I would be e to power r minus 1. So 0.05 here minus 1. And this value becomes 0.051271. So it's going to be 5.1271%. And then we can use this interest rate in this formula, right? So it's going to be 2,000 times 1 plus 0.051271 to the power 2. Okay? Then I believe you will get the same amount, which is $2,210.40. So in this example, I just show you 2 different ways to get the same answer. Okay? Okay. And here's the last example for today. Which is example 3-13. So how long will it take for money to double at 10% nominal interest, compounding continuously? So the formula for the single payment compound amount would be F equals P times F given P at R% over N, right? And which is same as P times e to power R times N, right? So here, the nominal interest rate is 10%. So here R is 10%. And N is unknown, right? N is unknown. But if we set present sum P equals 1, then the future sum F can be set to 2, right? F if P equals 1, then F becomes 2. Because your money will be doubled, right? So the formula, what you can have is 2 times X equals 1 times X times E2 R, which is 0.1 times N, right? Of course, here X is not equal to 0, okay? So here E2.1N equals 2. If you take the natural log on both sides, it's going to be 0.1 N log of E equals log of 2. And you know this is equal to 1, right? So from here, N is equal to log of 2 divided by 0.1. Okay? So this is going to be almost 6.93 years. So how you can answer the question? So it's going to take almost 7 years for you to double your money at 10% nominal interest compounded continuously. Okay? Okay, so I'm going to stop here for today. And next time I'm going to solve many of end of chapter 3 problems. Okay? So if you have time, please try to solve a couple end of chapter problems by yourself. And then you may want to double check it with my answer later. Okay? Thank you very much. I will see you next time. Bye-bye.